In this segment, we are going to solve some problems on counting principle. The first problem goes like, how many license plates can be formed where each plate will have three uppercase letters followed by three digits. Any of the letters or digits can be used repeatedly. So we are supposed to determine the total number of license plates under this condition. So the license plates will look like this. At first, there will be three different slots in which we will have to put some letters, and then there will be three slots in which we'll have to put three digits. And say here, for the first slot, how many options are there? 26. Why? There are 26 letters in English alphabet. And for the second slot, how many options will be there? See, any letter can be used repeatedly. That means the letter we use in the first slot, we can use it in the second slot as well. So the total number of available options for the second slot is 26. And the total number of available options for the third slot will be 26. And since we'll have to put in the fourth slot digits, so there are total 10 digits as we know, starting from 0, 1, 2, 3, at last 10, right? So here 10, here there are 10 box options, and there are 10 options here. So now what will we do? We can change this scenario and compare this with another. At first, we'll have to make some license plates. And before making a license plate, we are in X, and we'll have to accomplish task 1. What is task 1? Filling up the first box is task 1. Then we'll have to fill up the second box, that is task 2. We'll have to fill up the third box, that is task 3. We'll have to fill up the fourth box, that is task 4. Then task 5. And at last task 6. And after we accomplish all of those tasks, we'll reach Y. It means we will be able to make a license plate. So we are supposed to determine the total number of license plates. Isn't it similar to in how many ways can we reach Y starting from X? Yes, these are same. So we can see here, can we avoid any of these tasks here? Can we keep any of this box void? No. If we keep any of the 6 box void, that means the license plate will have 5 characters, right? But the license plate must have 6 characters. So we'll have to accomplish all of these tasks, and for each of the tasks there are 26 options. And as we see that since all of these tasks are mandatory, not alternative, that means their relation is related to AND. So AND refers to multiplication, as we can remember from the multiplication rule or product rule of counting. So here we'll have to use the product rule since all of these tasks are mandatory. And for the first task there are 26 ways, for the second there are 26 ways, for the third task there are 26 ways, for the fourth 10, 10 and 10. And since we'll have to use multiplication rule, since all of the tasks are mandatory, we'll multiply all of them, and at last we get that 26 cube into 10 cube. That means briefly 2260 whole cube. So there are total 260 different ways in which we can travel from X to Y. It means there are total 260 cube number of license plates in which these conditions are followed. So we notice here carefully that we used product rule because of all tasks being mandatory. So let's move towards the next problem, and it says that how many functions can we form from a set of n elements to a set of n elements. So as we know from the definition of function, function is kind of a relation, and in a function there is a set of domain and there is a set of codomain, and there is some kind of relation is mapped from the domain set to the codomain set, right? So here in this statement we get that the domain set has total m elements, right? So if this is the domain, there will be m elements, and say the elements are a1, a2, a3, like am. So here are m elements in the domain, and it says that how many functions can we form from a set of m elements to a set of n elements. It means the codomain will have total n elements. So this is codomain, and say there b1, b2, b3, and similarly there total n elements up to bn. So the question is how many possible functions can be built here. So let's assign a box corresponding to all of the elements of domain. Why did we assign these boxes here? Because we will fill up these boxes with the image of the corresponding elements. So we will put the image of a1 in this box. We'll put the image of a2 in this box. Okay, so here now how many possible options or how many possible images can be there for a1? See, it's simple that here there is total n elements, so any of these n elements can be an image of a1. So for the first box there are total n possible images or n possible options, and for the second box it refers to the image of a2. Will the number of images vary here? No, because as we can remember that in a function a1, a2, a3, if these are the elements of domain, then all of them can have same image. The function will not be an injective function then, but it will also maintain or follow the rule of being a function. So all of the elements of domain can have same image. So a2 here can also have the similar image of a1. So for a2 there will be n elements as well available. For a3 there can be n different images. For am there can be n different images. So here we want to determine how many possible functions will be there. So let's see if we can put any of these, keep any of these boxes void. Can we keep any of these boxes void? I must say no, because if you keep this box void, it means am doesn't have any image here. But if a relation has to be a function, it must maintain the rule that all of the elements of domain must have image. So you cannot keep any of these boxes void. That means all of these tasks are mandatory. Which tasks? Say starting from x, here we get that this is box corresponding to a1, this is a2, this is a3, and like this. At last there will be a box corresponding to am, which will contain the image of am here. So all of these boxes should be filled up, and each of them are different tasks which all of which are mandatory. So for the first task there are n different options, for the second there are n options, there for the third there are n options, and for the nth box there are total n options. So since all of these tasks are mandatory, so the relation refers to AND type relation, and as we know, AND always refers to multiplication, right? Multiplication. So here, if we have to determine how many possible functions can be mapped from the domain to codomain, the total number will be determined by multiplying all of the ways corresponding to this task. And how many n's will be multiplied here? Can you say that? Yes, it's easy. From the suffix we see that 1, 2, 3, there are total m boxes. So there will be total m number of n's multiplied here. And if we multiply m times, it means n to the power m. So the answer for this question will be n to the power m. It means there can be total n to the power m different functions that can be mapped from a set of m elements to a set of n elements, right? Okay, so let's move to the next problem. Here it says that, yes, we have already studied about it. Prove using counting principle that if A is a set where cardinality of A equals to n, you'll have to prove that cardinality of power set of A will be 2 to the power n. Let us recall the concept of power set. Here A is a set containing 1, 2 as its elements. So the power set of A is a set containing all of the subsets of set A. So it will contain all of the subsets of set A. So now let's see, how do we make a subset? In this case, since the cardinality of A equals to n, let's assume that set A has these elements A1, A2, A3, A4 up to An. So here, if we want to make a subset of set A, which is known as say S, we can either pick A1 from this set or we can reject A1 from here. We can either pick A2 or we can reject A2, because the subset of A must, and subset of A is not, it is not mandatory that the subset of A, S, will contain all of the elements of A. It can either reject any of its elements or it can also accept any of its elements. So if we want to build a subset of A, let us assign some boxes corresponding to these elements like before. And here in these boxes we'll put either tick mark or cross. What does it mean? If we put a tick here, it means A1 will be an element of set S, and if we put a cross in this box, it means A1 won't be an element of the subset S. And similarly, we can put a tick here or put a cross here. So for each of this box, there are two different options. Those are either tick or cross. So as we can see, for each of the box, if we want to make a subset of A, we can either take this element or we can reject this element. And let's see while making a subset S of A, can we keep any of these boxes void? Actually, we can either take an or we will reject an right here. But we cannot keep any box void because it is meaningless. It will either be in S or it will be rejected from S. So we will have to perform all of these tasks as well. So for each of these tasks there are two options. So from the multiplication rule again, the total number of ways in which we can choose, we can make a subset will be 2 multiplied by 2 multiplied by 2 multiplies 2. So there will be total this number of subsets of set A. So how many 2's are there? Since there are total n boxes, as we know here, n boxes, so there will be total n 2's multiplied here. So total number of subsets of A will be 2 to the power n. And as we know, power set of A is a set of all subsets of A. It means cardinality of power set of A will refer to the total number of subsets of it. And as we determined here, the total number of subsets of A is 2 to the power n. It means the cardinality of power set of A is 2 to the power n. So we have seen that how powerful is multiplication rule of counting. We can also solve this problem using the concept of permutation and combination, but we can also solve this kind of problem using simple counting principle. So that's all from this segment.